everybody, and welcome to Dark Matter Day. And we are going to have an amazing tour from our team at the Boulby Underground Laboratory, and we're all going to have a go at making our dark matter masks. So a big shout out to everyone that's joined us, but I do know we have some people that are joining us in Birmingham today, so hello to you. It is amazing to have you here, and we can't wait to see all the things that you are getting up to. My name is Lauren, and I am part of the public engagement team that work at the Rutherford Appleton Laboratory. So we are part of the Science and Technology Facilities Council. We've got labs all over the UK, but I am based down in Oxfordshire. But today we're going to be hearing about the lab, the Boulby Underground Laboratory, that is based in the northeast of England and is 1.1 kilometres underground. Now, they have been searching for dark matter since the 1990s in this lab, and it is an amazing place for research. So it is a deep underground science facility that's located 1.1 kilometres below ground in a working mine. So it's a very special place for science that enables a wide range of studies, requiring access to the geologically interesting and ultra low background in the deep underground environment. So just to show you a few little pictures. So in the top right, you can see a picture of what the mine looks like from the outside. On the left, you can see a little diagram to show you the mine on the surface going all the way underground to see our underground lab, which we'll be getting a tour of today. And into the clean room, you can see the outfits that our team have to wear to make sure that they stay clean in this underground lab. Now, I am going to show you very quickly a little bit of a video of how our team get underground. So you can imagine it's not just like going to a normal lab or to a normal office. You don't just drive there and then you're magically underground. We have to go underground in something called the cage, which is a lift that takes us underground. And we've got our team down there today that are going to be telling us all about the work that goes on there and helping us build and make our dark matter masks. So I'm going to show you their journey underground, how they got there this morning in the form of a beautiful video. Now, the video doesn't have any sound that you can listen to, so you just get to listen to my voice. So here we go. So you can see everybody on the surface getting ready to go into the mine, and that's Chris who's filming and taking us underground. So we're currently heading to the surface building where we will go underground, and you can see at this point nobody's wearing any lab coats. They're all wearing these bright orange suits, helmets, ear defenders, and other personal protection equipment. At this stage, they're heading towards the lift, known as the cage, that takes them to pit bottom, where the underground lab is located. So they're just coming up to the cage, and you can see Chris is going to show us one of his tallies. This is what they use to make sure they know who's in the lift, who's going down underground into the mine. You hand one in on the way down and one when you get back up. Now, the cage ride, the lift, takes 7 minutes to travel the 1.1 kilometres underground, and it only goes at very specific times. So if you miss it, you have to wait for the next one, which probably won't be soon. So don't forget your lunch. Now, once you reach pit bottom, it's about a 10-minute walk to the lab. Now, we've sped up this video so you don't have to watch their 10-minute walk to get to the lab. But you can see that away from pit bottom, it is quite dark. We've got these head torches to help us through the tunnels. Now, the layers of rock that are here are left over from the evaporation of an ancient sea called the Zechstein Sea about 250 million years ago. And they're very salty and dusty. And the mine stretches much further than what you can see here today. So you can see it's very dark, and we're walking and walking. Here we are coming up to the lab. We go into our mine area and then down the slope and into our lab. There we go. So I am now handing over to one of the team at Boulby. I'm handing over to Johnny, who is going to give us a little tour of the underground lab. So Johnny, I'm going to hand straight over to you. Welcome.
Hello, everybody. Welcome to our Dark Matter Day live link. Happy Halloween as well. It is the spooky season once again. So yes, right now, as you can hopefully see, I am 1.1 kilometers beneath the surface of the Earth, beneath the North York Moors, in Boulby Underground Laboratory. And I'm currently in our main hall. This is where we keep the majority of our particle physics and particle physics adjacent experiments. And I'm going to talk to you today a little bit about our lab, how we came to be, and I'll talk a little bit about dark matter, which is the phrase of the hour, dark matter. It is Dark Matter Day after all. I hope you're liking our spooky Halloween decorations today in the lab. So yes, I'm currently in the main hall of our lab. It is a 4,000-meter cubed underground laboratory in Boulby mine. I'll show you a little bit about what's behind me, and then we'll pass over later in the tour to see bugs, our material assay suite, and also our Mars yard, which is our outside experimentation area in the tunnels where we test Mars rovers and Mars rover technology. But first, let's talk about dark matter and talk about how our lab came to be. So back about 20, 30 years ago, a scientist from the University of Sheffield wanted to house an early generation dark matter detector in the tunnels of Boulby mine. That happened, and that was the first generation of our lab. We're currently on version 5 of our lab, and dark matter has been a part of what we do for as long as we have been operating. But why do you need to come underground to host a dark matter experiment? That's a great question. So when you're on the surface of the Earth, you're constantly being bombarded by cosmic radiation. This is radiation from outer space, and you're constantly bathed in it throughout the entire day. And it's not harmful. We have lived in it our entire lives. We've grown up in it. But it can be detrimental if you have a very, very sensitive particle detector, such as a dark matter detector. So by coming a kilometer underground, 1.1 kilometers underground in our case, most of that cosmic radiation from the surface is absorbed by the massive column of rock above our heads. In fact, here's a stat for you if you like your stats. For every 1 million cosmic rays that hit the surface of the Earth, only one of them is going to reach our underground lab. So where I currently am, it's a very quiet place in the universe, at least in terms of radiation. So let's talk a little bit about dark matter. That's the theme of today, right? So what is dark matter? Let's start by dissecting that phrase a little bit. Dark matter, 2 words. Matter is just the physicsy way of saying stuff, things that exist in the universe. And dark, we call dark matter dark because it's invisible. We can't see it with our eyes. You can't see it through a conventional telescope. It doesn't interact with light in the same way that normal matter does. And the most interesting thing about dark matter is that we think it makes up the majority of the universe. In fact, scientists estimate that 85% of all matter in the universe is, in fact, dark matter. So we think it's the overwhelming majority of the things around us in the universe. So dark matter, how do we know it's there? I guess that's the next logical question, right? If we can't see it with our eyes, then how do we know it exists? So this all starts in the 1950s with an American astronomer called Vera Rubin. And Vera Rubin was looking at stars, and she was looking at how fast they orbit the center of a galaxy. Now, our understanding of physics from Newton would tell us that stars near the center of a galaxy should orbit a lot faster than the stars near the outside of the galaxy. Think of it a little bit like swinging a tennis ball on a string. If you have a really short string, you have to swing the tennis ball really fast to keep that string upright. But if you have a really long string, you have to swing that tennis ball a lot slower. And we even see this in our solar system, actually. Mercury, a year on Mercury is about 80 days, but on Pluto, it's about 80 years. So what Vera did is she looked at the stars in our nearest neighboring galaxy, Andromeda, and she observed how fast they were rotating around the galactic center and found that actually stars were rotating a lot faster than they should be, particularly near the outer reaches of the galaxy. Okay, that's worrying. That's not what our understanding of physics would suggest. Okay, fine. Let's look at some other galaxies and let's see what happens to the stars in those galaxies. And what Vera Rubin and her team found was that actually this trend occurs in pretty much every galaxy that we can observe. That's a problem because that kind of messes with our understanding of physics. Why are these stars rotating and orbiting the center of galaxies faster than they should be. Okay, let's try work out why. There's two explanations here. Either our understanding of gravity is wrong, but we don't really want to question that because we've made some really accurate predictions based on our current understanding of gravity. Okay, so what else could be up? Maybe there's more mass out there in those galaxies than we can actually see. And this mass, it must be invisible because we can't see it through conventional telescopes. So that's why we call it dark matter. So there we have it. We know that dark matter exists. Let's try work out what it is. So scientists got thinking, could it be big rocky things that don't emit their own light? I mean, if they don't emit their own light and they're not near another light source, then perhaps that could explain all this missing mass. So things like exoplanets, things like dust, gas, and black holes in space that we can't see. So scientists made some estimations. They estimated the mass of all those things and they added it all up and then added a bit more for good measure. And they found that that explanation can't justify the sheer amount of mass that we're expecting to see. In fact, based on how quick those stars were rotating around the galactic center, there should be 10 times more mass out there than we can actually see. Okay, so what else could dark matter be? Well, our current best guess is that it's a type of particle that we call a WIMP. WIMP stands for Weakly Interacting Massive Particle. And we think this is a new type, a fundamental particle that we've not yet observed in physics. So the game then becomes, across the international dark matter community, can we detect it using particle detectors? And then that brings us back to where we are today. Boulby Underground Laboratory. Boulby Underground Laboratory is a deep underground science facility, one of only about 15 in the world, perfect for hosting low background particle physics experiments, such as dark matter detectors. So in the past, we hosted a dark matter detector called Zeppelin-3. And in fact, there's another one behind me now, currently no longer operational, called Drift. And Drift was a real pioneer for its time, as it was a directional dark matter detector. Looking for dark matter particles follows this approximate through line. You'll build a detector. It will probe a certain region of particle parameter, looking for dark matter. So say, for example, you'll build a particle detector. It might look for dark matter particles that are really heavy and really likely to interact. You'll run it for 10 or so years. You won't find anything, and you can cross that section off your parameter space. Dark matter particles can't be heavy and easy to detect. You'll then build a new detector with better technology, and you'll look for dark matter particles that are a bit lighter and a bit harder to detect. You'll run that for a few years, and you still won't find dark matter. And this general process of crossing off potential properties that dark matter particles could have is what dark matter detection projects generally look like. So this is another dark matter detection project that we have in our lab. This is called, this is a detector from the NewsG collaboration. NewsG stands for New Experiment with Spheres-Gas. This is a dark matter detection collaboration looking at using spherical dark matter detectors to look for dark matter particles. This one in particular is using isobutane in the middle of its detector to try and look for low mass dark matter particles. So dark matter particles that are lightweight. I used to refer to that as light dark matter particles, but I realize that's a bit confusing. Light dark matter, low mass dark matter particles. Okay, so I'll walk you down our lab here, and I can talk to you a little bit about some of the other science that we have in our laboratory. I will mention now, we are currently in a class 10,000 clean room. So if you remember, I mentioned earlier, the reason that we come underground to do very sensitive particle physics is to escape cosmic radiation, which might interrupt the very sensitive detectors that we have. The same applies to dust and dirt. Everything is slightly radioactive. So in order to make sure that our particle detectors are operating to their fullest capacity, we have to make sure they are housed in a very, very clean environment. So in a little while, I'll hand you over to Beth, actually, and she'll show you bugs, not just yet, but in a little while. And that is a class 1000 clean room, so even cleaner. So I'd like to talk quickly about this experiment that you can just see back there behind Andrew in a castle. This is an experiment called Cellar. This is not related to dark matter, but I want to mention it to demonstrate the wide variety of science that you can do in a clean room facility 1.1 kilometers underground. So Cellar was a experiment which stood for Subsurface Experiment of Life in Low Radiation. And it looked at how does life fare in low radiation environments. So we know that life generally doesn't like being in high radiation environments, but what about when you come a kilometer underground in an ultra low radiation environment? Does life benefit from being in low radiation, or is it actually hurt by being in low radiation? So what this experiment, done in collaboration with the University of Edinburgh, looked at doing was getting 2 colonies of identical bacteria, putting them in 2 separate compartments in this shielding, and comparing them. How do they grow when you expose one to an artificial radiation source? And what the experiment found is that actually life seemingly doesn't benefit from being in a low radiation environment. So actually, it's not harmful to be down here, but it's also not beneficial to be down here. And projects like this are really interesting because it then leads into more questions. So what about random genetic mutation that has given rise to evolution throughout the millions of years that life has existed on planet Earth? Has that been a product of being in background radiation? And also, how does it affect humans long term? These are all questions that hopefully will be answered in the future of underground science. So I'd like to finally show you around our LEC area. LEC stands for Large Experimental Cavern. And it's a pretty large experimental cavern. This is our LEC area. And behind me is Button, or the shell of Button. Button is a 30,000 litre water-based Cherenkov detector, looking at detecting antineutrinos. And the neutrino is another type of fundamental particle, and the antineutrino is its antiparticle. This is currently just a steel tank, which was constructed in the first quarter of the year. Sorry about the noise. I hope you can hear me. I'll try and speak loud. And it's looking at detecting Cherenkov light, which is a light given off when an antineutrino interacts with, for example, a big column of water. And this is another type of particle physics that we host in our lab, which isn't just dark matter. Oh, hello. I think my audio is being funny because I'm stood next to something very loud. Oh, can't hear the background noise. Okay, that's good news. That's good news. Yeah, sorry, the preview in my chat said, this sounds excellent. We can't hear ... And I got quite worried you've not heard me for 10 minutes. Yes, so more particle physics, very interesting. And this leads me on to talk about the future of our lab. And what other experiments can we possibly host? I mean, Button is by far the biggest physically experiment that our lab has seen. I mean, it's about 3-point-something meters tall, I think. This entire cavern is 6.9 meters tall. So I can't really stand next to it, but it would be very humbling if I did. So let's talk a bit about the future of Boulby Underground Laboratory. And I hope I can make you excited by talking about this. So dark matter detectors are getting bigger and bigger and more technologically advanced and more exciting. And there's a new one on the horizon, and it's called XLZD. It is a big international collaboration that combines multiple dark matter collaborations. Xenon is the X, LZ from Lux Zeppelin, the current world's best dark matter detector in America, and Darwin. And this is a really big international effort to build an even better, even bigger dark matter detector to hopefully, once and for all, find it. And there are multiple labs around the world which would be a great site for it. And we would love to be the lab to host XLZD. But in order to host the world's best dark matter detector, we're going to have to expand in many ways. And one of those is getting a bigger lab. So currently, excavations are happening in Boulby Mine to dig us a new lab, what we're calling the phase 1 lab that you can see behind me, the stage 1 lab, is going to be about 5 times bigger than our current facility, with multiple caverns of this size. And that will be used, if we were lucky enough to get XLZD, as a site to construct in clean environments the components necessary for this great dark matter detector. Then if we do get XLZD, we'll build another, even bigger lab, a stage 2 facility, which will be bigger once again. So exciting times here at Boulby. We're hopefully going to be hosting some great dark matter projects in the future, bringing such interesting science to the UK. So I think I'm nearing the end of my time slot here, and I don't want to blabber on for too long. So I'll hand you back now. And if anyone has any questions about what you've seen in the main hall, please remember to put them in the chat, and we'll be answering questions at the end.
Fantastic. Thank you so much, Johnny. We've had a couple of questions that I wondered if you would be happy to answer now, just while I get my slides ready to show you about dark matter masks. Would you be happy with that? Just one.
Yeah, let me.
Perfect. So there's 2 questions that I quite like the answer of. I quite like the question of that says, are you allowed to eat bananas before going in the mine because bananas are radioactive? And how big is the lab? Would you be happy to answer those for me, please?
Of course, I sure can. So yes, we are allowed to eat bananas, and you're right, they are slightly radioactive, as are Brazil nuts. But no, what we eat is not restricted before we come underground. I like bananas, so I'm very pleased that that is the case. How big is the lab? That's a great question. So it's a bit hard to convey on video sometimes. So this tunnel, this main hall that I'm currently in, you can see the perimeter of it there. It's about 3 meters tall and about 8 to 9 meters wide. So it is about the width and height of maybe a classroom. And then this extends for quite a length, maybe about 100 odd meters, the extent of our main hall. And that continues beyond the roller doors out into the Mars yard, which Ed will be showing you around in a little bit. So it's quite spacey. It's definitely far from claustrophobic.
Fantastic. Thank you. I am going to share our next little activity. So hopefully you are all here and ready to make your very own dark matter masks. And I know some of the team at Boulby are also going to be making some to show you at the end as well. But just a little reminder. So as Johnny said, that we don't really know what most of the universe is made of. Scientists think that there's something called dark matter, which we can see the effects of, but we've never been able to catch it. And many people think that dark matter is made up of tiny particles called WIMPs, weakly interactive massive particles. And if it is, we know that WIMPs are heavy, they pass straight through almost everything, and they aren't electrically charged or magnetic. So what we want you to do is have a go at making your very own dark matter masks, a little bit like this one. So hopefully you have got a paper plate or a piece of paper that you can cut into a lovely circle shape big enough to fit over your face. The first step that we'd like you to do is make sure you cut out some eye holes if you want to wear your mask and be able to see it. And then also cut some little holes at the side so that you can tie some ribbon or some string through so that you can attach it like a mask. Now you might need a grown-up to help you cut your eye holes or your string holes. But make sure you get some help with those, and then you are ready to do the most important part of the dark matter mask, which is to turn it into dark matter. And now, as I said, we don't really know what dark matter looks like, so this is up to you. Use your imagination to come up with something amazing. So just remember that we know that WIMPs, those weakly interactive massive particles, are heavy. They pass straight through almost everything. They aren't electrically charged or magnetic, and they're very mysterious. Okay, those mysterious particles. So have a little think about what you might want to do to convey that. So maybe you want to stick lots of things on it. Maybe you want to draw some beautiful patterns. What do you think dark matter looks like? Maybe you're helping our scientists. Okay, so there we go. Have a little go at working through that. You can do that while you're watching the rest of the tours, and we'll come back at the end and we'll see what some of our team have made. And we would absolutely love it if you would take a picture of your dark matter masks when you've finished and send them to us so we can see them. Okay, so I'm going to stop my share. Hopefully you've remembered all those things and you're ready, you're on it. Brilliant. Amazing. So I think I am now handing over to Beth, who is in bugs. Are you with us, Beth? Amazing. And we'll hand over for our next part of the tour. Welcome, Beth.
Hi everyone. First of all, happy Halloween and happy Dark Matter Day. My name is Beth and I'm coming to you from Bugs, which is our Class 1000 clean room, as Johnny said. And since it is a Class 1000 clean room in Bugs, we have to wear extra PPE, hence the hairnet and gloves. And also we wear extra boot covers, a different hat for this clean room, and the men wear beard net. So first, I'm going to tell you why we have bugs and why we need bugs for all these experiments. So as Johnny said, for dark matter detectors, scientists will go underground so that they are shielded from the cosmic radiation, and we actually have 1,000,000 times less interference from cosmic rays underground. That means the particles that they are trying to detect, there isn't all these other particles getting in the way and screwing up their results. But since everything is radioactive, the actual materials they are using to make these detectors will be radioactive themselves. So when they turn the detectors on, they will be detecting radiation from the walls of these detectors and other bits of equipment inside it. So it makes it hard to tell whether they've found dark matter or just something off the side. So what they do to solve this problem is they find out exactly how much expected radiation they should have from the detectors themselves, and they can call this the background radiation, and they will subtract this from their results that they find through their dark matter detection. And to find these radioactive properties, we have our germanium detectors that we have in Bugs. And basically, these germanium detectors will assay these samples of the materials they are using for about 2 weeks, and we can produce a report telling them exactly what radionuclides are found in these samples. So here are our detectors. This is Uplethem and Kirklethem and Merrybent. And if you have noticed, if you know about mines or local mines to this area, you will know that they are named after them. We also have Rosebery here. Rosebery is world leading at detecting lead-210, so it is very popular, and lots of experiments want their samples screened on Rosebery. These are Loonhead, Challoner, Belmont, and Lumpsea, and then our XIAs Ormsby and Kettleness. Yeah, so they are named after the local mines in the area around Boulby. And how they work is, so they are what's called a semiconductor when they are cooled to a really low temperature. To get these down to this temperature, we use liquid nitrogen. Don't play with that at home. And they are stored in these dewars here. And some of them are also electronically cooled. And because this is a semiconductor, when the source is emitting photons, it will interact with the detector and release these charge carriers, which have an energy corresponding to the exact radionuclide that is in it. And then it will turn into an electrical signal, and we can read them off our computer and analyze these results. And then we can produce a report for these samples to send back to the scientists who are making these incredible large dark matter detectors all over the world. Some of the samples we have handled as Boulby staff are samples from LZ, which Johnny mentioned earlier, which is the current most sensitive dark matter detector in the world, and it is part of the XLZD collaboration. and Super K, which is a detector in Japan, which won a Nobel Prize for detecting neutrinos. And this is really interesting and really exciting for people who work at Boulby, because all the samples and all the pieces of equipment that hopefully will find dark matter have been in our hands first, have been handled, put through these detectors, and we work on these reports, which means these samples started out here before they were in these detectors, before they were looking for dark matter. They were right here, 1,000 meters below Boulby, in Boulby Lab. It's really incredible to think that these things are that important. So the first germanium detector was actually put down here back in 1990. And since then, we are constantly upgrading our facilities here at Boulby and constantly trying to get a lower background and more sensitive detectors to help out with these experiments. So it's really exciting to be a part of that and to handle those projects right here in Boulby. So thank you for listening to my talk about the detectors in Boulby. And now I am going to pass you back to Lauren.
Amazing. Thank you so, so much. I think I am just going to change the spotlight. Perfect. So before we hand over to Ed, I'm just going to check in how everybody is doing with their dark matter masks. If anyone does have any questions, please do pop them in the Q&A if you want to ask anything. We can try and answer them for you, and we will get people to answer them, and we will have some time at the end to go through with everyone about that as well. Okie dokie. So just to give you a little bit of a hint in case you need it with your dark matter mask. So here we go. So here is the one that we made earlier. Okay, you can see we've got some very mysterious looking wiggles coming out the top. We've stuck on some beautiful pipe cleaners. We've got some bits of foam. We've used some pens. Have a go with what you've got. See what you want to add. Don't forget, have a think about how you would like to make it represent dark matter. Think about it. Be as imaginative as you can. And we would love to see them at the end, and we will have a look at our teams very soon. So we've had a few questions in the chat. Is anyone from Boulby around able to pop on their camera and answer a couple of questions for us? Fantastic, Johnny. Amazing. So our first question, Johnny, just for 5 minutes, is how much germanium is in a detector?
How much germanium is in a detector? Wow, that's a good question. Oh, I might have to field this one to Beth if you're still there. Beth is our currently on call as the germanium detector expert here. Beth, are you here? Are you able to give us an estimation of how much germanium's in a germanium detector?
So basically, the inside of the germanium detector, there is a crystal, and then it is covered in other things like copper and stuff to make a low background. I think all the germanium crystals are a different size to detect different energies. Some of them you can put the sample around it, some of them you rest the sample on top, and some of them you can put the sample inside. And some of them are able to detect really high energies because of this. Some of them are lower, but the amount is probably like, I think it's a couple of kilograms worth that is in the crystal inside the germanium detector to find these.
Yeah, and I think the one in Rosebery is about similar size to a hockey puck.
Something like that.
So it ranges to about 1 kilogram and a bit down to smaller.
Excellent. And one final question before we jump to Ed in the mine, in the Mars yard. How many people work at the Boulby Underground Lab?
Great question. So, we've expanded quite a lot over the past year, but I'd say we're probably sitting at about 20 to 22 people. 22, I want to say. Yeah, and that's a big range from managers who are working in health and safety and science and facility maintenance, all the way down to apprentices and placement students. So large range of people that work here.
Fantastic, thank you. I think it is a great time to hand over to Ed, and they are in our Mars yard to finish our tours of the lab today. So Ed, over to you. Thank you.
Thank you very much, Lauren, and welcome to the dark and mysterious tunnel. Happy Halloween, everyone. You've seen a lot of incredible science inside in the laboratory, very clean, very shiny. But sometimes you can forget that you are actually underground, whereas this is what the majority of the tunnels in the mine look like, or don't look like if you've got no lights on, because it is absolutely pitch black. There is no light getting this far down from the surface. Fortunately for us, in the area that I'm standing, we do have some lights that we can illuminate the area with. So we'll get those switched on in just a second. But yes, happy Halloween. Who knows what's lurking in the dark corners of the tunnels? Ooh, there we go. There's some light for us. So, as we've said earlier, we come underground to get away from radiation, primarily cosmic radiation that exists on the surface, comes from space, particles interacting in the upper atmosphere, and they cascade down from the upper atmosphere, they reach the surface, and they get absorbed. And the deeper you go underground, the more of these get absorbed. So we are here primarily because there was an existing space. There was this mine where we could use some of the old tunnels. The tunnels that the lab are in are mostly not built specifically for the lab. They were pre-existing tunnels, which makes it a lot more, feasible to host a lab when you're not having to come all the way down just for the lab. The space was there already and we can make use of it. So we work in close collaboration with the operators of the mine, and they are mining this area for rock salt, different types of rock salt. The tunnel that I'm in right now, the wall is pretty much NaCl table salt. It is the sort of stuff you could grind up and put on your chips if you wanted. And yeah, so the walls around me are about 98% pure salt. But the stuff that they're actually looking for is called polyhalite. And this is a type of rock salt that's used as fertilizer, and it gets shipped all around the world to be used as a fertilizer. Originally, they were mining for potash, which is another type of rock salt, that's potassium chloride, I think, that also was used as a fertilizer. So it's a whole load of agricultural stuff, the purpose of the mining here. And this salt was left behind by an ancient sea, as Lauren mentioned, called the Zechstein Sea. And this evaporated and reformed and evaporated a number of times, approximately 250 million years ago. And as the water evaporated, it left behind the salt. These salt layers then get compressed and crushed, and over millions and millions of years, they get pushed further and further underground. And that is the level that we're standing in today, just over 1 kilometer underground in this very salty environment, very dry, because the salt sucks a lot of the moisture out of the air. It's very hot. We're closer to the Earth's core here, so the rock temperature is in excess of 30 degrees. The spot where I'm standing right now is about 34. And the further away you get from the lift shaft, the hotter it gets, because they're blowing fresh air in constantly to keep it cool and to provide enough oxygen so that the deeper parts of the mine are actually able to breathe. So we come underground, we get away from this radiation, we exist within this incredible, unique geology. So we not only use our incredible high-tech clean room to do fantastic modern science, we also have a lot of scientists that are interested in the actual geology around us. And this ranges from all sorts of things, from geologists who want to study the rock directly to astrobiologists and space scientists who are looking for life on other planets. So sounds a little bit crazy to go underground if you want to study space, but there's a lot of reasons that actually make this area really good for studying space exploration technology and the search for life on other planets. So we have this really unique geology. It's incredibly salty, it's incredibly dry, it's been left alone for several million years, but there are still little microbes, little bacteria that can be found within some of the water that's coming up into the mine from lower down. and you also can find fossilized microbes within little pockets in the salt. So as the water dries up and the salt crystals start to form, you might get little pockets of air trapped within that, or little pockets of water trapped within the crystals. And any bacteria or microbes that were trapped in there, you might still be able to find remnants of them even 250 million years later. So when we go to Mars or we go to the moon and we're looking for signs of life, the very first thing that we look for is water, because on Earth, all life as we know it requires water in some form or another. So the very first thing we do is go, is there water? Did there used to be water? And on Mars, at least, we believe that there used to be liquid water a long time in the past, and that has since evaporated and potentially left behind a whole load of salt beds. So that's kind of similar to the situation that we have here, right? So if there ever was life that existed in that water and is now trapped in the salt, then the sort of techniques and the technologies that you're going to use to look for it and to explore for it, you can test right here in the UK, in Boulby, without having to send your, your rover all the way to Mars only to find out that the technology doesn't work. So you need to be able to test it first. So in this very tunnel, we have had scientists from NASA, from the European Space Agency, and from all sorts of universities and institutes. They've come underground to test all of these different experiments. We've had a prototype Mars rover driving around in the tunnels, testing itself. And we've had lots of like individual experiments that will hopefully go on future Mars exploration missions. So one of the next big Mars missions is a rover called the Rosalind Franklin rover, which has been delayed a couple of times, but 3 of the experiments that are on that rover were tested here at Boulby, which is incredible to think that something that's been in the tunnel right here is going to end up on Mars. That's astonishing. We've also had an actual astronaut underground practicing how you would do things like sample preparation and sample collection outside of a spacecraft, on Mars or on the moon, things like that. Yeah, so we also have these very space age futuristic domes that we've got in the back here. And this is another type of space exploration experiment. And this is looking at the development of medicine for outside of Earth operations. Currently, there is not a huge amount of facility for treating wounds in space or on Mars. If you had a serious accident, we don't really know how you'd be able to treat that if you're on Mars, because it takes a lot of equipment to set up a proper hospital. If you've been to a hospital, you've got so many different pieces of machinery and all of the different supplies that they need. So one of the first things that we need to look at is what's the minimum amount of stuff you can take and still have an effective hospital? Because every single thing that you send into space, like every gram, is exceedingly expensive. You need the rocket fuel to send it into space and then all the way to Mars. So you really, really want to be able to work with an absolute minimum amount of stuff. So how could you potentially grow things on site, on Mars? How could you use the existing resources that were there to develop and build things? And that's a lot about what's being looked at in these domes is, how can we do medicine with a very minimal amount of supplies? It's also just looking at how biology reacts in very different environments, right? So we understand how medicines work on Earth, but if we're looking at environments with different gravity, environments with very different radiation situations, all this sort of stuff, it could affect how medicines actually interact with the body. And that's something that we need to understand as well if we want to send humans to other planets. So no aliens yet, though. It's all about the search for life on other planets. We have also got scientists who are looking at pure geology experiments, as I mentioned earlier. So I'll just talk about that very briefly to end us off. So the experiment that's going on in the little tunnel behind me, this is looking at large-scale energy storage. So the rock around me is salt, and salt is a very good rock for containing gases because it moves ever so slowly and it sort of seals gaps within itself. So you can use it to store very large amounts of gas. And there is an idea that using gas under high pressure could be used as essentially a massive battery. So when you are generating more energy than you immediately need, perhaps because it's a very windy day and the wind turbines are generating a lot of energy, you need some way to store that. And traditional batteries, like lithium ion or lead acid batteries, they're just not very effective on the massive scales that we'd be talking about. So we need different solutions, and one of those is the idea that we could pump gas into a big salt cavern and use the compression to store the energy to then release it later when you need it. That is some of the additional science that we have going on outside in our tunnels here. I'm going to pass us back to Lauren now, and I'm going to go back inside where we've got some nice air conditioning, and hopefully we can answer some more of your questions. Thanks very much, everyone.
Amazing. Thank you so much, Ed. That was really, really interesting. So what I'm hoping now is that some of our team at the Boulby Underground Lab have had a go at making their very own dark matter masks. So I am going to spotlight them as well, so you can see we've definitely got Johnny, and Johnny will show us his dark matter mask, and Beth, I think, as well. If either of you would like to talk through your dark matter mask and tell us why you've chosen the things you've done, then you can. But if you just want to show us, that's okay as well.
So I'll show mine quickly first. So if I had the option to use lots and lots of glitter, I would have done, but that's not really great in a clean room. So I've gone a bit more primitive. This is mine. This is the center of a galaxy. This is a black hole with its accretion disk. These are different solar systems around the galaxy. And then this around the outside here is dark matter. Because I didn't mention this in my main hall bit earlier, but scientists think that dark matter clumps in halos around galaxies. So this is my dark matter mask halo, galaxy halo. Hang on, there's my eyes. There you go.
Amazing. I love it. Beth, have you got one to show us as well?
I don't have one here in bugs, but Bradley and Alice might have.
Yes.
Oh, yeah, that's the one I started earlier.
Perfect.
Gonna show you all.
Amazing. Would you like to tell us a little bit about why you designed it the way you did? No, either. I don't mind who.
So mine is basically what we would see in a dark matter detector if we saw dark matter interacting. So basically we see the light coming off the interaction and then a secondary light signal from the electrons that are produced from the interaction, and we detect it with these sensors at the top and the bottom.
Amazing. Thank you, Alice. That's awesome. Bradley?
Mine's not as technical as that. I just picked some nice colours. It's very unfinished.
That's okay. You've been listening and helping with the tours as well. You know,
Yes.
we're very impressed. That looks very, very cool.
Thank you.
Ed, have you got some to show us too? No, you're just here to answer questions. That's okay. Fantastic. So what I'm going to do is spotlight all of you in the Boulby teams so that we can ask you a few questions, and you can take it in turns to answer some. But we've got some amazing questions here today. So the first few I'll ask you are a little bit to do with dark matter and antimatter. A few people have asked, is there a difference between dark matter and antimatter? And if so, what is it?
So very simply, we can describe a lot of the matter in the universe with a standard model of particle physics, which is like a zoo of all the different particles that we know exist and we have observed. And for each of those normal matter particles, there is an antiparticle associated with them. So the electron has an antiparticle called the positron, and that applies to the other particles too. Whereas dark matter, we think, is an entirely new type of fundamental particle, either a class of particles or maybe we don't know. So that's separate to antimatter. It's an entirely new class of particles with new properties.
Amazing. And then somebody else has asked, do you work with antimatter at the Boulby Underground Lab?
So we have experiments that do investigate technologies for detecting types of antimatter. So I mentioned it briefly earlier. Button is the big metal tank at the end of our lab, and that's a new experiment, and that revolves around developing technology for detecting antineutrinos. As to whether we have a bucket of antimatter in the corner, no, we don't. But a lot of our experiments do involve detecting antimatter to understand its properties.
Did you have anything to add, Ed? I saw you unmute for a moment. Perfect. And then our next question about dark matter says, how old is dark matter?
That is a really good question. So I'm going to answer first with the theory of dark matter. As Johnny said, the theory of dark matter is about 80 years old. It's when it started to be taken seriously, the idea that, that there was some sort of missing mass in the universe. With the current theory of dark matter, WIMPs, as we've been talking about, they are only a little bit younger than the universe. So they formed in the very, very early universe, very shortly after the Big Bang. So dark matter would then be just about 13.8 billion years old.
Anything to add, anybody? I feel like that was pretty good answers. The next few are a little bit about the lab. So who would like to answer? So somebody wants to know, do you do public open days? Can children come to the lab? Can people just come and visit when they like? Is that allowed?
Sadly not, no. You have to be over 18 to come underground, and even then, being able to come to the lab is a very logistically demanding process. Coming underground, coming on site at the mine, having people supervise you to be around the lab is quite logistically demanding. So we don't do public open days, unfortunately, but we do our absolute hardest to get out there into the world and share what we do through events such as this, online, webinars, virtual tours, and you'll also find us sometimes doing outreach with schools in the local area or nationally, and at other public events occasionally throughout the year.
Amazing. And somebody's asked, it can be a bit of a maze in the mine. How do you find your way around? How do you know where to go?
So luckily for us, our lab is not too far from what we call pit bottom, which is where the bottom of the shaft is when we come down in the lift. So we have all memorized the way to the lab. We have headlamps on when we're going through the mine, so we know where we're going, and we always will have a supervisor who is like certain of the route with us. The rest of the mine, I think they've mined about 1,000 kilometers in total, but the miners know where they're going and we know where we're going. So it's not often that someone would get lost. I don't think anyone's ever got lost because we also have trackers on us. The overseers on the surface who are like tracking where we are will always make sure that we're where we're supposed to be, and we can call them or they can call us if there's ever a problem.
Very, very, very good. So Ed, you mentioned when you were out in the mine tunnel that it was a little bit warm and you were looking forward to getting back into the air conditioning. Can you tell us a little bit how warm is it down there, and are you feeling much cooler now you're back in the lab?
Yeah, definitely. So as I said, directly outside the lab right now is 34 degrees, which is, yeah, warm, and it's much cooler in here. We keep it at a constant 20 in the lab, or as close to constant as we can. As you get further away from the lift shaft, the temperature goes up as well. So the where the miners are actually working, because it's, you know, so far away, and because they've got machinery running and all sorts, it can easily be 45 or more degrees. It's very, very warm, very unpleasant to be working in. Yeah.
Yeah, it can be nice and hot, but we're glad you're in the air conditioned part at the moment. So we've got a couple more minutes, and we've had a few more questions about dark matter. So I thought now would be a good time to ask those. We've had a question that says, if dark matter is so elusive, maybe it doesn't exist. What do you think?
Well, we do know it exists. We see the effects of it gravitationally on other objects. So, like I mentioned earlier, stars will rotate and do rotate around the center of galaxies much faster than what they should be. And because we're pretty confident in our theory of gravity, that leads us to believe that there is missing mass out there that we can't see. But there's also more evidence for the existence of dark matter. We can see gravitational microlensing effects from the presence of mass that we can't see. So again, it's multiple different things leading us to a single conclusion.
Amazing. And a question from Birmingham. Again, hello to Birmingham that are joining us. Can dark matter be formed artificially?
Theoretically, yes. So the type of experiments that we are doing are so-called direct dark matter searches, because we are looking for dark matter particles that would interact with stuff within our detectors. But other places in the world, like the LHC in Switzerland at CERN, they are trying to produce dark matter particles through very high energy collisions. If you've heard of the LHC before, the idea there is you recreate incredibly high energy conditions similar to what we had seconds after the Big Bang. And hopefully the particles that come out of that might also be dark matter. So yes, that people are trying to artificially create dark matter through that process as well.
It's very cool. And almost our final question. If you find dark matter, what will you do with it?
Well, I suppose this is a bit like, what did we know electricity would do for us when that was discovered and understood centuries ago? Who knew that I'd be sat in front of you now over a video call using the internet, talking to you through an electronic eye. It's one of those things. We are looking for it to understand our universe, but it's hard to say what we'll use it for in 100, 200, 1,000 years.
Yeah, very true, very fair. And then one last question that says, how far away is the dark matter that Boulby is trying to detect? Is it in the lab?
So, as Ed mentioned earlier, yes, it is in the lab in some ways. So when we build a dark matter detector, we're looking for a dark matter particle's interaction with the stuff that's in our detector. And we think that these dark matter particles that we are trying to detect will be passing through our lab, passing through us, and we're just waiting for that very rare chance that it might interact with something that we can then see. So yes, it can be found around us.
Fantastic. And then our final question, I think, fits in very nicely with the fact that it is almost lunchtime. Our final question is, do you eat in the lab? Can you eat when you're underground?
Yeah, we can eat when we're underground. It's very important because obviously, yeah, we always have biscuits. There's constantly a supply of biscuits. Sometimes we would do like a longer day where we would go down at about 9 and come up at about 5. So we definitely do need to eat. However, if you get your food on the surface, there is no shop underground to go and buy our lunch from. So you'll be waiting until you come back up to have your dinner.
It's very true. But they've got there's always many biscuits underground in the lab, and a kettle and water for making teas and coffee. So don't worry, our lovely team at Boulby are not going hungry. But I think that brings us to the close of our event today. So thank you so much for joining us, everybody. We've really enjoyed having you. Please do send us photos of your masks that you've got. And as we wave goodbye, I'm going to ask if the team at Boulby, if you can put your masks up to your faces if you've got them, and we'll give everybody a big wave, and just a massive thank you all, to all of us for joining us. So thank you all so much, and we will see you again soon. Goodbye.